today. I also came from Boston. There's a great crowd over there, but I gotta say, Lisbon is beautiful. I've eaten amazing food this week, so thank you all for that. And I'm here to talk to you about my experience moving from physical product development to digital product development. How many people here work in software? Okay, good majority. And hardware? Like 1, 2, all right. Some combination of the both? Okay, well, great. Well, my hope for this talk is that I can show you what it takes to build hardware products and software products and how we can combine best practices from both to be better product people. So, 2 years ago, I left a job that I loved in mechanical engineering. I wanted to learn how to build products for the connected world, and immersing myself in internet technology seemed like the fastest way to get there. A lot about my work changed. I traded in CAD models for code branches and SolidWorks for Jira tickets, and very quickly found myself kind of neck deep in this unfamiliar alphabet soup of CTRs and ETLs and A/B testing, and it was like learning a whole new language. And a lot about my day-to-day life changed, too. I was moving from a company of 19 people to a company of 500 people. Within 6 months, my inbox was already twice the size of my 4-year-old email. I stopped using paper. I had 100% fewer power tools, but 100% more ping pong. It was kind of a weird trade-off, but I'll take it. As a mechanical engineer, I worked at a company called Fixed, which is also in Boston. And Fixed is a product design and development firm that really specializes in solving very tough technical problems for our clients. So we would spend a lot of time building core technology, and that meant really understanding the problem that they had at hand. My background is in physics, so this meant a lot of research, doing a lot of lab instrumentation work, modeling things, and then trying to understand how we can design something to fix their problem. So that would mean sketching an idea, modeling it in 3 dimensions, developing prototypes, testing those prototypes, and doing a very iterative process. It was very technically focused, but a lot of what we did was product management because we were a consultancy. At Kayak, what I do is very different. I focus on running a lot of experimentations, so there's still a lot of data analysis, but I'm building a product that's accessed by millions of people every day. I'm working on a lot of machine learning, improving the algorithms that we use on site, understanding the usability challenges that our users have, and then developing the commercial strategy for the company. So how many people here are familiar with Kayak? All right, that's what I like to see. So Kayak is a travel search engine. When you search on Kayak for your trip, we are searching hundreds of other sites to bring all of the results for you in one place so that you can compare prices and find the option that's best for you. And if you don't know where you want to go, then we can show you where you can afford to fly within your budget. We build a lot of tools that make sure you're finding exactly what you're looking for. So that's advanced filters, sorting options, maps, providing a lot of information all in one place. And then we have a suite of free tools that you can take on your trip with you. So if you flew here today for this conference, you could use Kayak Trips to keep your boarding pass, your hotel information, your transportation information, all in one place as you're on the go. So as I moved from building these physical objects to these software products, the types of things that I was building is very different, but the approach to problem solving is very much the same. So if I asked you to figure out a way to cross this gorge, you might think, oh, okay, I need to design the best bridge. And what is really the best bridge? Well, it's a bridge that's very durable, can hold a lot of people, will be long-lasting, very accessible. So with those sorts of definitions, the best bridge is actually just a stretch of metal, as long as you can imagine, that crosses this gorge. But you will never see a bridge that looks like that, because that would be prohibitively expensive. So problem solving and engineering, it's never about building the best solution, it's about building the best solution within your set of constraints. And I like to think of every solution as a trade-off between impact, risk, and cost. If you're looking for an ideal solution, that's something that would be very impactful. If you solve this problem, it would really make a difference for the users. An ideal solution would have a very low risk of failure and very low cost. Unfortunately, these are kind of like the unicorns of solution space. They don't really exist. What you see more often is an incremental solution. So this is something that's not really very impactful, very low risk, very low cost. So easy to implement, but doesn't really move the needle. As product managers, we're on the hunt for the powerful solutions. So these are the ones that are delivering that impact that you seek, but they usually come with a pretty high cost and a pretty high risk factor. And powerful solutions are usually so costly because it means you're working on something that's hard. And if you're trying to solve a hard problem, it's costly because you don't yet know how you're going to do it. So you're going to have to try a lot of things. And the chances are that your first idea for solving this problem is not the right one. So if you were to productize your first idea and go from start to finish, you're going to incur a lot of cost. So our goal is to make the powerful solutions look more like ideal solutions, and the best tool for doing that is iteration. So very much like what Adam was saying, let's build something small, let's test it out, let's get the feedback. And if you can try a lot of ideas with an SVP or an MVP, then you do not incur the cost of productizing the wrong thing. And you can eliminate very quickly the approaches that are just not viable. So, iteration, while it's a very important tool, it looks extremely different for hardware and software products. And those differences are really driven by three main factors: capital, scale, and lifecycle. And these are the areas that I think really distinguish hardware and software product development. So for the remainder of the talk, I'm going to walk through each of these, give you an example of products that I think really accentuate the differences, and then talk about what each realm can really take from the other in these three domains. So what do I mean when I talk about these things? Capital, I'm really saying, like, what do you need to get going on a product? What tools are absolutely necessary? What do you have to invest in to build something that you can deliver? When I talk about scale, I'm saying, okay, how do you move from that first idea to something you can launch? And then once you launch, what sort of growth can you anticipate? Is this something that's going to have a very wide user base? What sort of scale can you use to offset those capital costs? And then, of course, life cycle. Where does iteration come in the development process? What are the traditional pitfalls of developing a hardware versus a software product? So starting with capital, if you ask a coder what they need to get going on a project, the first thing you're going to hear is a laptop. And if you ask a few mechanical engineers, you will not get two matching answers, and I know this because I tried. So these things, they both start from the same place, but they diverge very, very quickly. Mechanical engineers gave me answers like hand tools, a glue gun, a 3D printer, a CNC mill, soldering iron, breadboards, calipers, duct tape. That was my favorite. Software, just got a computer. So how do you reconcile these differences? How can you play in the hardware space if you need all of these tools up front? Where we see the gap closing is with rapid prototyping, and that's these tools like 3D printers, laser cutters. If we look at the development of personal computing between 1974 and today, we see that over a window of about 20 or 30 years, we went from market introduction to market ubiquity. Today, the average person has a computer in their home. We're looking at about the same window for 3D printers. The first 3D printer came out in 1986. And we don't really have the same market ubiquity. The average person does not have a 3D printer in their home. So personal computers, while they're a very powerful tool for building software, they're also a very powerful tool for accessing software. Now every person can just access a suite of really incredible tools. I'm a little skeptical that 3D printers will ever follow the same track. I don't think that they'll be sitting in people's homes and that people will be printing their own spoons every day. I don't know, I've been wrong before. But I think where 3D printers and rapid prototyping deliver the most value is in helping enterprises and companies get ahead of both technical and product risk when they're developing a new product, and that can be very powerful. So how can we use these tools, and how can we push them to the limit to really close the capital requirement gap between hardware and software? Let me give you an example. When I worked at Fixed, I worked on a project called PharmaCheck. And this company came out of a group at BU that had developed chemistry to check whether malaria pills were counterfeit or substandard. And this is a very big problem in developing nations. The state of the art for testing malaria pills today is using an HPLC column. Those are tens of thousands of dollars. They're very stationary. They're really not a reasonable solution for these developing nations that need to check the quality of these pills on a regular basis. It was cost prohibitive. So using an Arduino, which is a $20 microprocessor, a laser saw, which is a build-it-yourself laser cutter, and FDM 3D printing, we were able to build a tool that productized this chemistry for only 10% the cost of the state-of-the-art, but it achieved 90% the same results. So before we wanted to go from start to finish with this idea, we wanted to understand how do users in these nations use a product like this? What are the pitfalls of this kind of test? So this is what our first prototype looks like. This went out, we built 3 beta units, it went out to Ghana. The whole thing was built into a camera case. The wires were held together with tape. There was hot glue, spray paint, but the whole thing was powered by a pneumatic pump that ran the chemistry across the photodetector that was attached to an Arduino that could interpret the signal from the reaction and print the results to a touchscreen. Using this rapid prototyping technology, we were able to figure out how we could get the chemistry to be in the field with actual users and then get their feedback. So we were moving the learning up very early in the process. These rapid prototyping tools had helped us make hardware development look a lot more like software development, where you can get feedback on how something's actually working. So where do I think these two worlds can combine? Well, I think that software can really learn the value of the right tool from hardware. That's something that hardware does well. How many times did you have a very difficult problem that could have been solved just by investing in a little bit more hardware, a few more servers, instead of throwing expensive developer time sort of chasing this Sisyphusian task? What I think hardware still needs to learn is the importance of lowering the barrier to entry. So how can people play in the hardware space if you need all of this stuff to get going? And I think we see good progress here with things like makerspaces, fab labs, crowdfunding. You no longer need to have a ton of cash on hand to get going, but we still need to keep moving in that direction. Okay, so scale. So if capital is sort of the taxing of product development, I think that scale facilitates profit. It's the takeoff. So if my hardware example was kind of about detecting whether or not malaria pills were good, my software example is about detecting whether or not something is a hot dog. So, how many people have seen Silicon Valley? Great. Well, then you know that they've built an app where you take a picture and it will tell you whether something you're looking at is a hot dog. In the TV show, they have this app. In real life, they also built this app. And the only thing they used to build the app was a laptop and a GPU. And they wrote this really incredible Medium post on how they did it. They put all of the processing power on the user's device. So with very little capital investment, they were able to build a product that could reach millions of people. So this is a silly example, I know, but I think that it really illustrates how the margins in software can be so gainly. With very little upfront capital investment, you can reach millions of people, a huge amount of scale. So one thing that hardware has an advantage over software is that it's easy to anticipate the maximum number of users because you can only have as many users as parts you've produced. You're making a discrete number of things, you can't have more than that. In software, you need to scale a little bit more elastically. An example from Kayak, here you see daily searches from Florida. Every single day, same amount of searches, very regular, very periodic, until a hurricane is approaching, and then the number of searches from that area skyrockets. So good software products can respond to these changing demands. Hardware, while they can anticipate the maximum number of users, it's very hard for them to understand the demand for their product. Even just this week, we saw that Snapchat way overestimated the amount of spectacles that they would sell. Now, it's very hard to scale back from having produced all of that hardware. So I think what the two worlds can learn with regard to scale is that hardware needs to be a little bit more modular with how it scales. Like I said, it's very difficult to scale back. I think one of the most challenging aspects of predicting hardware demand is that hardware faces threats of commoditization that software really doesn't. I think software can learn the importance of improving feature quality over feature quantity. So as PMs, we certainly know that feature creep is a huge thing. Scope creep comes in all the time from all parts of the business. Hardware has an ethos that's really focused on improving the efficiency of things you've already built. So reducing the friction in a bearing or improving the efficiency of a battery. And I think that software would do well to adopt that ethos. Okay, so last but not least, lifecycle. So timelines in these two development worlds and the role of iteration really diverge. Both kind of start from the same place, which is understanding the problem, validating your customer, and then brainstorming. But from there, the development cycles look very different. So software, you might start with a proof of concept, move to a prototype, start on an MVP. At that point, you can get something in the hands of users. Then you get data about how they're using it, feedback about what they do and don't like, and that's really just the beginning of your iteration cycle. The life cycle never ends after that. You're constantly improving. Hardware has a lot more constraints. You can't push real-time updates to something that's tangible and in users' hands. You have to be absolutely certain that it's going to work once it's being produced. So this is where rapid prototyping is closing that gap a little bit, because you can get something that looks and feels like the final product into the user's hands much earlier. After you've prototyped something and you've iterated on it and you're pretty sure that you're ready to go to production, then with hardware, you need to go through another round of design. Then you're designing the tooling. That's usually tens of thousands of dollars. You're getting the first parts back from the manufacturer. That usually involves shipping something across the world a couple times. You need to make some changes. You ship it back again. And this cycle can go on for months. After you have parts that you're confident in, then you begin assembling them. And that could be at another factory, another location. Then you enter the distribution chain. So this life cycle is much, much longer until you get something finalized in users' hands. If you look at the Kayak website 10 years ago, it looked like this. We release code to the site multiple times a day, and now it looks like this. So the iteration is never over for us, even 10 years later. At any point in time, we're running tens of experiments, hundreds of experiments, to make sure that we're having a product that meets our users' needs. This is a photo from the first round of the PharmaCheck device. On the left, you see our very, very first prototype. This was using a $15 pump, off-the-shelf jars, connected to an Arduino. Again, you see the duct tape, you see the foam. And this was really the test that we ran to see whether these types of tools could get ahead of the technical risk associated with this product. Could we use these plastic parts to achieve the same level of precision that we needed to get the chemistry to work? After we really validated the idea that way, then we moved to something that looked more like this. So on the right, you have the beta prototype that went out to users in Ghana. You see a user interacting with it, and we got feedback about what was confusing, what was hard to install. And this is really just the start of something that we're iterating on before it's finally productized. So after this, we'd move to maybe, again, injection molding these parts, cutting them on tools, and then assembling everything together, and then shipping it out. So you can see that the requirements for producing hardware are a lot more involved. So I think what software gets right is getting products into users' hands early. And what hardware gets right is the importance of a first impression. How many times have we seen a software product launch and just they really didn't get the launch right? It's very hard to back off of that first impression. You have to completely reshift the user's expectations. Hardware understands that once you have something in a user's hands, it has to work and it has to be right. So what does this all mean? I think that in the product development process, if you can move the learning up early into your cycle, you can get ahead of whatever your limited resource is. So for software, because the overhead is so low, the limited resource is usually time. How long is it going to take to develop something? How long is it going to take to compile it, to build it, to load it, to run it? In hardware, the limited resource is usually money. The cost to make something, the cost to cut tools, the material cost, the cost of goods. But as we know, time is money, so chances are your limited resource is really just some combination of the two. So I hope that this talk really explained to you how the capital, scale, and life cycle differences in hardware and software drive the difference in economics between these two worlds. And I think that if you can move the learning early up in the process, bring iteration into your product development cycle, you can get ahead of figuring out whatever your limited resource is. Value is really unlocked when you can keep the cost of trying unusual ideas low, because when you're trying crazy ideas, it's much more likely that you're going to land on those powerful solutions. Thank you very much.